so to speak. We've got a theorem coming up here. So one of the big things that we took away from Lagrange's theorem is if you have a group of order n and a subgroup, then any subgroup, the order of the subgroup must divide the order of the group. So in particular, the order of any element in the group divides the order of the group if the group is finite. If you have a divisor of the order of the group, does that necessarily mean that you have a subgroup of that order? And the answer in general is no. But there is a very famous positive result theorem. This is called Cauchy's theorem. If G is a finite group, and we'll say the order of 3 is equal to n, and P is prime, and P divides n, then there exists element G of order. This is kind of a nifty little theorem. It doesn't solve everything for us, but in the case that you have a prime that divides the order of the group, then you know for sure that there's an element of prime order. So for example, if you have Rubik's group, so this is just the group of arrangements on a 3x3 Rubik's cube. The order of this is equal to 11 factorial, 8 factorial, 3 from 8 to 12. Cauchy's theorem tells us, do I know that I've got an element of order 3 to the 8? No, I don't. And well, actually, for this one, I actually do not have an element of that order, but it's a possibility, but I don't know anything. But I know Cauchy tells us there exist elements of order 2, 3, 5, 7, and 11 in this group, because those are the primes that divide that number. So I know for sure that you have to have elements of the Rubik's group of those elements. Lagrange tells us, in fact, also that there's no element of order 13 or any higher prime. Yes.
What is that word before the 7?
Says, yeah, it's spelled. Okay. Well, that's what Cauchy tells us, right? Cauchy's theorem says that there exists elements of those orders, those prime orders. So this is actually a really cool proof because it is one of the really first looks at an application of group actions. So let's go through this. Let's prove this. I'm going to start by doing the following. I am going to consider the set A1, A2, AP, or AI is a G, and A1, A2. Where here I'm denoting the identity of G as well. So what have I done? I've created this set for the purposes of my proof. What is this? Well, these are, just think of these as P tuples. It's just a list of P things. All of these things are in G, and I've got one caveat, and that is the product of the entries, the product of the elements in the P tuple has to be the identity of G, right? Let me point out that this set is not empty because here's one element in my set S. 1, 1, 1, all the way across the board. Everybody agree with that? Because the product of all the ones is going to be, everybody okay with it? So let us count the elements in an S. That is my first task here. How many elements are in it? Well, anybody think of a way to count these?
P no.
Sorry?
Is P no?
Well,
Or is it just
all we
some-
know about P is it's a prime. And yes, P is going to factor into this because I got P coordinates. Think of it this way. For the first A1, A2, A3, A P minus 1, A B. If I didn't have this condition right here, the number of elements would be n to the P power, where n is the number of elements in G, right? Everybody agree with that? Because I've got n choices for the first coordinate, n choices for the second coordinate, n choices for the third, and so forth. So it would be n to the P power if I could pick anything, right? In other words, without this condition where the product of all of these have to be the identity. Everybody agree with that? So how many is it when I impose this condition? Actually, I claim it's just one less than power. It's the number of elements that you P minus 1 power. Anybody explain why? Yeah.
P minus 1, you can do anything. And then the last one just has to be the inverse.
That's exactly right. You can do anything you please here. I don't care. You can put any of the n elements, any of the n elements, any of the n elements there, right? The last one is the condition. You just need to make sure that the last one is the inverse of the product of these, right? So the last one has to be and that meets our condition, right? So you've got complete freedom. You can do anything you want on the first P minus 1 coordinates, and then make sure that the last one makes this work, right? This product has a unique inverse, and there it is. Everybody understand why that's the case? Okay, so notice that it's divisible by P as n is divisible by P. N has a factor of P in it, so that means n to the P minus 1 has a factor of P in it as well. In fact, it's got more than just one, but we'll only need one. We'll see that later. Okay. So what I'm going to do is I'm going to let the group CP act on I'm going to define a group action of C mod P on the set S, the set of P tuples. And how am I going to do this? Well, if J bar is in CP, then J bar acts on A1, A2, AP by shifting it that many steps. So in other words, this would be 1 plus J plus J AP minus 1, AP, A1, AJ. Right. So all I've done here is, so what we do is, so for example, 0 bar doesn't shift it at all. 1 bar shifts A2, AP, and then it ends up at A1. 2 bar shifts at 2 spaces and so forth and so on. Everybody see what we're doing? We're just using the fact ZP has P elements in it. This has P elements, and I'm just shifting. This thing just tells me what to do. Notice that if K is equivalent to J mod P, then J bar and K bar act identically on AP tuple. Right? Because these are exactly P long, right? So in other words, 0 bar doesn't shift this at all. P bar shifts this P places, which is the same as not shifting it at all. Right? Everybody okay with me? So this is a well-defined action. It's easy to see that, right? Also notice that I bar operating on J bar AP equals I bar plus J bar operating on A1, A2, AP. And let me explain this. Yes, I'm sorry.
Can you re-explain about why the J is shifting A1, A2, but not the APs?
Oh, it does shift them.
Okay.
Right? So what happens is this just counts. So what it does is it shifts up further into the cycle. It reaches AP and then it starts over again. So when it does the shift, it's in the same order, right? Think of it like a clock. A1 is connected to A2, A2 is connected to A3, A3 is connected to A4, and AP is connected to A1. So when it does a shift, let's see. Right. So when it does a shift back, it pulls the AP down and then it starts over after it.
But there's no like P plus J as like an index.
P plus J equals J. Right? That's the point here. Right? Because if J and P plus J are equivalent mod P. So that does the same thing. Shifting something by J and shifting something by J and then P is the same thing as just shifting by J. Because there's exactly P things in the cycle. Yes.
This may just be me not quite remembering what an action is, but the result of the action would be in S, right? Not in ZP.
The result of the action should be, it still be an S, yes.
It's just taking on the properties of ZP, and that's when you
Yeah,
act
the
on
ZP,
something.
right, the ZP is turning the crank, what it does. But every time it acts, this new thing is still in the original set S. Because remember, it's the same elements, right? It's just they're in a different order perhaps. And so their product is still going to be what you want it to be, right?
how can we guarantee that the product is one without knowing that S is associative or commutative?
Well, the group is associative. Remember that, right?
We define it as such, or did?
I mean, like if the group isn't abelian, how would we guarantee that it's still one? Is that what you mean? See what you mean.
Is the group abelian though? We never defined it as abelian.
Well, so, no, the group is not, in fact, the group is not abelian. In general, you wouldn't expect. But I think I can address your question here. So suppose you have A1, A2, AP equals 1. Right? Now, multiply on the, whichever side this is, the left by A1 inverse. Right? Now multiply on the right by A1. And does this address your, so in other words, the product is still 1, even though, yeah. I think, did I address the question that you're getting at? And actually, that was a good question. He was worried about this. He was worried about, hey, Jim, you scrambled the order now. How do you know that product's still 1? But it's precisely because of this right here. Everybody okay? Okay. Let me also point out that this composition holds. So what this says here is I shift this by J and then I shift that by I. That's the same thing as shifting the whole shebang in the first place by I plus J, right? So this is in fact a group action. So ZP acts on the set S. So this group action actually partitions the set into equivalence classes. So this group action partitions the set S is equivalent classes. And the equivalence relation is just if one thing is a shift or another. So we will declare X1, X2, XP is related to Y1, Y2, YP. If one of them is a shift of another. If there's a is a shift. Now, let me make that more precise. That is, there exists an I between J between 0 and P minus I. Such that yi x to the I plus j. And what do I mean by I plus j hat? This is just the integer in the range from 0 to P minus 1 that is equivalent to I mod D. So in other words, all we're saying here is if I can do a J shift on this to get this. That's what it means to be equivalent. So for example, A1 through AP is equivalent to A2 through AP than A1 because this one's a shift of this one. Anything that's just a shift of it, that's what I mean to be related. This is pretty easily seen to be an equivalence relation. because anything is equivalent to itself because it's a shift by nothing, right? You shifted zero, right? If you shift one of the if you shift one of these sequences by I steps to get the next one, then shifting this one backwards I steps will get the original one, right? And if you shift this sequence to this one by stepping it up I, and this sequence to this one by stepping it up J, then to get from the original to the end point, you just shift by I plus J like this. So it's an equivalence class, or I'm sorry, it's an equivalence relation. Now, this means it's an equivalence relation and partitions S into a set of equivalence classes. This is something that we've already seen. So S is partitioned by the equivalence classes. Under my shift relation. Now I'm going to make a bold claim. I claim that if you have an equivalence equivalent contains either P elements or one of S. So I've got this S, this set of all these P tuples, and their product is the identity. There are two kinds of equivalence classes. One of them contains, well, one possibility is the element contains P elements. The other possibility is it contains one. Now, off the top of my head, I can't think of one necessarily that's got P elements. But one way to do it would be if all the elements in that list were different, right? Because if they were all different in there, then every shift is going to be different. So that's a possibility. But for sure, I can think of an equivalence class that only has one element. Can anybody give me an example of an equivalent? Yes.
Everything's the identity.
Everything is the identity. One's across the board. Any shift is the same thing. There's only one element in that equivalence class, right? You shift it P times, it's always the same thing. That's an example of an equivalence class that only has one element in it, right? From the same point of view, there certainly can be no equivalence class that has more than P elements in it, right? Because any one of the equivalence class is every possible shift of this. And how many shifts are there? At most P, because there's only P coordinates. You can put the A1 here, 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 all the way up to P, and that's it. So certainly there's no more than P elements in any equivalence class. There could be an equivalence, there could be one P elements. We'll come back to that. There's certainly an equivalence class, at least one that's got one element in it. All right. So let's suppose there exists an equivalence class with, people say, suppose there's an equivalence class containing the element x1, x2, x3, x1. Okay, suppose there's an equivalence class and it contains that element, and suppose that there's less than P elements in the equivalence class. So in other words, some shift, not all shifts are different, right? So we must have, without loss of generality, there's this J. Here I want J to be between 1 and P minus 1. Such that x to the I equals x, yeah, plus J. For all I between 0 and P minus 1. Oh, wait a minute. Actually, that's so in particular, so let's start with x1. This is x 1 plus j. But you should get the same thing when you shift again. So it should be x1 plus 2j. And if you keep shifting, because this thing has less than p elements in the equivalence class, this should go all the way up to 1 plus p minus 1. Okay. Now, let me point out, and here's where the prime part comes in, and the prime part has to come in. Now notice that if you have, notice that if 1 plus mj bar equals 1 plus kj bar. So if those two are the same, that means that the difference between oh yeah, and I'm going to say with m less than k. If this is true, then m minus k is equivalent to 0, or I'm sorry, times j is equivalent to 0 mod. For these two to be the same mod p, that means that m minus k times j has to be equal to 0 mod p. But j only right up 1%. So m minus k times j is equal to a times p for some a in the integers. But p doesn't divide j. P does not divide j, and p is prime. So p divides m minus k. And that's impossible if m is less than k. Possible. M less than k. So our conclusion here is that, so all these elements must be the same. So all elements X1, X2, XP must be the same. So the equivalence class is of size 1. So this is an important conclusion to come to, and that is, in this situation that we have with our set S, with these P tuples, your equivalence classes either have P different elements, it's got P elements in it, or it's got exactly 1. And that's really the linchpin of this proof, because we can now do some counting. We can write S is partitioned by these equivalent classes. So if I want to count the number of elements in S, I can write this as P plus R, where P equals the number of elements in a class of size P. And R equals just the number of elements, equivalence classes of size 1. So every element in there, every element in S goes into one of these categories, right? It either comes from an equivalence class of size P, and so there's a multiple of P for every one of those equivalence classes, or it comes from an equivalence class of size 1. And of course, each equivalence class of size 1 has only 1 element. Now, notice that the early observation that we made, S is divisible by P. And this is also divisible by P. Because remember, S was actually n to the P minus 1 power and n divided P, so this has a factor of P. This is some number of equivalence classes, each with size P, and they're all disjoint. So this is also a multiple. So R is a multiple of P. Everybody with me? Yes.
Can you explain why that is following from what you just said?
What, R is a multiple of P?
Yeah.
This is a multiple of P, right? So think of it this way. There's a factor of P here, there's a factor of P here, pull them out. That means that that factor of P divides R. Everybody okay with that? So R is a multiple of P. So the number of equivalence classes of size 1 is a multiple of P. And it can't be 0. 0 is certainly divisible by P. Can somebody explain why? There must be at least one equivalence class of size 1. Can you identify it? I agree with that. So that R can't be 0. It's got to be at least 1. So R is greater than or equal to P, because the next multiple up from 0 is P, right? But there's only one equivalence class is full of the identity. So there must be an equivalence class that looks like this, with X not being the identity, right? Because these equivalence classes of size 1 all have to be the same across the board. Therefore, X to the P. Because remember, all these sequences satisfy this, that the product of all those is the identity. So we have proved that if you have any group of order n and you have a prime dividing the order of the group, then there must be an element order P. There's no guarantee for any higher power of P or anything like that. Well, what we will find out soon, so this is a bit of a spoiler alert, is if you have a prime power that divides the order of the group, then there is a subgroup of any prime power that divides the order of the group. But there's no guarantee of an element of that order. Okay, any questions on that? Yes.
So was this whole thing to prove that any of the equivalence classes contain either P elements or one element?
Well, right. We reduced it to accounting because you've got some equivalence classes have P elements. They're all lumped in here. So the number of elements in here is a multiple P, the number of elements in here. And you've only got one type of equivalence class, and that is the ones that look like this, that only have one element in it. Then we showed that the number of such equivalence classes must be a multiple of P and not 0. So it's got to be at least P. So there's got to be at least one equivalence class that looks like this with X not equal to 1. And so X to the P equals the identity.
So that proves any equivalence classes contains P elements or one element of S?
Well, yes, we did prove that along the way, that any equivalence class of this set under this relation has either P elements or one element. Okay, other questions? Okay, so that was kind of a first look at an application of group actions. So really what made that work is the fact that ZP had this nice little symmetric action. You know, you basically took these P tuples and you kind of shifted them in order. And we got something out of it. We showed that any group of order n where n is divisible by a prime has an order of that prime. We'll plot some of this later as well. Let me give you the following definition. This is kind of a definition notation thing. Let H, K, and G be subgroups. Here's the definition part. When you see this notation here, HK, what do I mean by this? This is just crap that looks like this. Things of form HK, where H lives in H and K lives in K. Now that is just a construction at this point. Let me point out, I don't know anything about this other than it's a set, right? It's just I don't claim that this is a group. It certainly does contain the identity though. Can anybody explain why? That's right. The identity lives here and here, so you just take identity, right? So it's certainly there, but it's not even clear that this is closed under multiplication, and in general, it's not. Because if I have H times K and then I multiply by H1 K1, there's no guarantee I can write that as a single H times a single K. It's not clear at all. This is a set. Sometimes this will be a group, and we're going to explore when that is. But this is it's often important to be able to count such sets like this. And that's what we're going to do here in the first theorem. Let H, K, and G be subgroups. I want to count the number of elements in HK, this set right here. Any ideas what the answer should be here? Anybody want to take a stab at it? Naively, I might think, well, I've got however many elements there are in H to choose from this, how many elements there are in K to choose from this. Is this, yes,
You have to subtract the intersection or some form of the intersection to get rid of all the.
That's right. That very astute. And in fact, here, since it's actually here, you can divide. So take the number of elements in H times the number of elements in K, divide it by the number of elements in the intersection, and you will be good to go. So this is kind of an important counting bit. So let's see why this is true. The first thing I want to notice is let let me kind of make an observation using this concepts business we did before. This HK should be the union right? I could go through piece by piece and just take okay, H1K, collect that. That's a coset, isn't it? Right? In fact, since H is an element of G, this is just one of the left cosets of of K and G. So I can just collect the elements of this coset, collect the elements of go through all the H's and collect that, right? Now, the good thing about cosets that help me count here is any two cosets, HK and H prime K, one of two things happens. They're either exactly alike or they're disjoint. Y'all remember that about cosets, right? So we're going to have to sort out which ones are different. So we need to find the number of distinct left cosets of the form HK. And if I can count those, then I'll be pretty good to go. So suppose that we have two left cosets. So first, I want to remember this observation here. Note that H1K is equal to H2K if and only if anybody remember the condition we need for those two cosets to be same?
One and H2 have to be the same.
No, it's looser than that. If and only if H2 inverse H1 is in K. Certainly that's true if H1 and H2 are the same, but this is more generally true. Remember, that's how we tell two cosets are the same if the inverse of this times this, if it's in, right? So in this case, notice that H2 inverse H1 is in K, right? Because the two cosets are the same. And they're in H because both H1 and H2 are in H. So they're in K intersect H, which means that these are distinct, which means these are the same coset in K mod H. H intersect K is equal to, that's not K1, it's H2 H intersect K. So we just need to, so the number of distinct cosets of this form cosets G of form HK coincides with number of cosets in H of H intersect K. Right. And so now, now we've got it. So to count this up, we're counting up the number of cosets, which is H and then of course every coset has K elements in there. And of course yeah, big slide. And of course this is H K H intersect K. Here, I was implicitly assuming this the entire time. Of course, I mean for H and K to be finite, because otherwise it doesn't make any sense for me to divide something. Okay, any questions on that? Okay, I'm gonna leave you with something to think about. So here's kind of the next theorem that we will build to. We'll go through this. It's not too difficult to prove actually, but this will be something for you to think about. And it's a fairly simple characterization, but this is useful. Let H and K and G be subgroups. Then HK is a subgroup of G. This might seem like a strange condition. If and only if the set HK is the same thing as the set KH. So in other words, if you reverse the roles of H and K, you still get the same subset. Now, be careful here. This doesn't mean that either group commutes. It doesn't even mean that the elements of H and the elements of K commute. It just means those two sets are the same when you put them together in different orders and collect the elements. So think about why that might be true, and we'll discuss that next time. Any questions? You put